Imagine a gas so violently reactive that it attacks almost everything it touches. It doesn't wait for a spark or a flame. The moment it makes contact, it simply incinerates whatever is in its path. This pale yellow gas terrified early chemists. In the race to study it, several researchers, who became known as the fluorine martyrs, were severely poisoned, blinded, or even killed by the toxic fumes. Because it is so intensely aggressive, pure fluorine actually naturally exists freely in nature. If it were somehow released, it would immediately rip apart the molecules of its surrounding environment to form new chemical compounds. Yet the exact same element that chewed through early laboratories and injured the people trying to study it is currently sitting quietly in your home. You brush your teeth with it, it's woven into your smartphone, and it protects modern spacecraft. How did we take the most fiercely reactive element on the periodic table and turn it into a quiet, life-saving tool? To understand that, we have to look past the violent explosions and zoom way down to the underlying rules of atomic attraction. Fluorine is the most electronegative element discovered, meaning it has an extreme hunger for electrons. It wants a perfectly stable outer shell of 8, but only has 7. To fill this glaring gap, fluorine aggressively rips that missing electron away from almost any nearby atom. When millions of fluorine atoms perform this desperate microscopic theft all at once, the result on a human scale is a massive release of energy. This creates the intense heat and macroscopic explosions that make it so dangerous to handle. This atomic hunger is exactly why it took decades to isolate. When chemists tried to trap the gas, fluorine immediately stole electrons from the glass or metal containers, eating right through the walls. It reacts wildly with metals, sulfur, carbon, and even those solid materials that scientists previously thought were completely unreactive. Forcing fluorine to exist entirely on its own is fighting its basic chemical nature. It simply refuses to be left alone. Eventually, chemists realized something crucial. If you simply give fluorine the one electron it so desperately wants, it stops attacking. It becomes completely satisfied. And because its grip on that stolen electron is so powerful, once fluorine bonds with another element, it locks into place. It forms some of the most stable, tightly bound chemical compounds in the universe, fiercely repelling any outside interference. We see the most common result of this in this vintage photograph of a woman cooking. That pan is coated in a synthetic fluorine compound. Because the fluorine is completely satisfied and locked tightly to carbon, it refuses to react with the food, the grease, or the intense heat of the stove. The same chemical aggression that makes pure fluorine a hazard is exactly what creates the extreme strength of its stable compounds. This chemical stability allows for high-precision manufacturing. Look at this photograph of a semiconductor facility. Technicians here use fluorine gases to etch microscopic circuits onto silicon wafers that run our smartphones and computers. We even attach fluorine atoms to the active ingredients in modern medicines, helping the drugs survive the harsh acidic environment of the human stomach so they can reach the bloodstream effectively. In the energy sector, fluorine compounds are relied upon heavily to process and refine uranium for nuclear fuel. And as you can see in this historical photo of a rocket in a wind tunnel, aerospace engineers depend on fluorine-based materials that are tough enough to survive the punishing friction and extreme temperatures of flight. Without the ability to control this reactivity, modern microchips, medicines, and aerospace materials would be impossible to produce. Fluorine functions as a chemical paradox. Its extreme reactivity is the same property that makes its compounds stable enough for use in medicine and heavy industry. This element operates according to rigid physical laws, demanding respect and precision from those who wish to use it. If you enjoyed uncovering the hidden secrets of the elements, make sure to like this video, subscribe to Atomic 118, and turn on notifications so you don't miss our next deep dive into the periodic table. Until then, stay curious and keep exploring the atomic world.